Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Last two classes we have just started our discussion on introduction to high temperature materials. We tried to look at, or we have discussed two classes on various aspects of these high temperature materials, means the basic characteristic that are demanded for a material to be exploited as a high temperature or ultra high temperature materials, and how to improve in terms of alteration of the microstructure, how to improve the high temperature capability of the materials. Okay. Mostly like alloys, like precipitation strengthening, dispersion strengthening and so on. And today we would like to see that what are the alloy or material specifically used as high temperature material. Okay. And we would like to classify those material from the very beginning days where people tried to explore material to be used as higher temperature or elevated temperature. Now, let us have a look at this diagram. Here we have plotted the demanded life of a component with the temperature or operating temperature of a material. You can see that around 10 to the power 6 hour required for using a steam turbine, okay, because repetitive times, long time duration, the steam turbine has to be used. Very similar like petrochemical industries or industrial turbines, and relatively lower life is expected in a jet engine. On the other hand, for re-entry spacecraft, where maximum we use those re-entry vehicles for 1 or 2 times, means those vehicle which goes outside our earth atmosphere, go into the space and again re-enter into our atmosphere with a higher oxygen content, and therefore, due to high friction and oxidation on the surface and so on. So, there are many other problems due to which we need to develop materials, and here maybe maximum 2 or 3 times those similar material can be used. However, for these hypersonic re-entry vehicles, yes, the operating temperature is quite high, like 4000 degree centigrade. However, at the very beginning we would like to start with the material that is exploited for this purpose, means we need a very high life for very long time in a petrochemical industry or in a boiler, in a steam engine and so on. So, where we can use, or maybe some of the heating elements that is used for furnace equipments. Okay. So, these are like lamp filaments also. So, these are very important aspect of the material. Now, let us see that from very common alloys, how different high temperature alloys has evolved. We all know about steels, right. So, steel is basically an alloy of iron and carbon. Okay. However, the alloyed steels are used for very other important engineering applications. So, here there are 4 major category of steels that are exploited for let us say the higher temperature application, like ferritic steels. Yes, ferritic means basically the microstructure contain ferrite, heat resistant steel, martensite creep resistant steel. Mostly we know, yes, MS temperature is close to room temperature, and how we are talking about having a steel to be exploited something like 500 degree centigrade in a boiler, and the microstructure should contain martensite. Yes, by alloy addition we can do that. Okay. We will discuss today. Now, austenitic steels are very much well known with a high formability. Okay. And we can refine those microstructure, tune the microstructure to achieve very high strength or in a very aggressive corrosion environment. Okay. Or some of the steel with some transformation characteristic, phase transformation, control transformation steels there we can use. On the other hand, for a very long time, use of a internal combustion engine that we all know, where the cast irons are used. Okay. Those are called as nickel hard and so on, high nickel containing cast irons are used with, let us say, gray cast iron where friction is very less, or spheroidal graphite cast iron or austenitic cast irons. So, these are also cast irons are also used quite long time, let us say something like 200-300 degrees centigrade. Now, from a steel to a very advanced alloy like super alloys has been derived for this steam turbine. It does not necessarily mean that steels are no longer used, means high temperature steels are no longer used. It is used more and more day by day due to the development of alloy addition and so on. So, these are also a class of advanced material along with the super alloys. So, mostly these nickel based and cobalt based super alloys are often used. However, there are also some derivative of iron nickel content super alloys which are also used for higher temperature. Now, another important aspect here is use of intermetallic for high temperature application, where titanium, aluminum containing intermetallic, where aluminum has a very low solid solubility or very limited range of solubility, we call them as aluminite. And you can easily understand what is the purpose of using aluminum content intermetallic, because we expect at higher temperature those intermetallic has usually higher melting temperature, it will give us a good strength at elevated temperature. On the other hand, aluminum will react with the surface oxygen and form alumina, which is expected to provide a good oxidation resistance. So, that is basically the purpose. Now, there are some speculative intermetallics people call, and be more specific, these are silicide, means some metal with some silicon containing compound. Okay. So, here silicon and this metal, these intermetallics use for like molybdenum disilicides use for our heat in a furnace the heating element, and the purpose is that using these silicon containing compounds, if it react with oxygen, then we basically get a silicon dioxide which is a glassy nature and protect the surface of those heating element. Not only heating element, people are thinking about the silicide to be replacing a component for the super alloys or beyond nickel based super alloy. Along with that, the other high temperature materials are like cermet. Cermet, you know, which is ceramic, cer comes from ceramic and metal the met. So, these are the material like tungsten carbide and other metal matrix and so on are often used, or high temperature ceramic and composites. So, we will go by step and we will try to look at what are those material which are very much important to discuss in this particular course. So, let us say let us start with the steel which are called as the ferritic steels. So, name itself says that the microstructure should contain the ferrite. But before going to that, I said that the use of these high temperature steel, one of the large amount of these steels are produced for power plant. In a power plant, what we really do? We basically increase the temperature or above the vaporization temperature and boiling temperature of a water. Okay. And we use these steams and send it to a turbine which generates the electricity. Now, from our very basic thermodynamic concept, you would realize the more and more higher temperature of the steam will give us a better and better efficiency of the Carnot cycle. Means we can extract more amount of energy out of that energy input. Okay. And on the other hand, what will be the benefit of that? if we can extract more energy, then we will automatically have for a particular power output lower carbon dioxide content generation. So, at the very beginning the demand is basically higher efficiency, means Carnot efficiency, and lower emission of the carbon dioxide, which is called as HELE. However, these days another supportive technology has been developed in order to reduce the carbon dioxide from the atmosphere which came out of a power plant. So, this is called carbon capture and storage, CCS technology. Now, to understand the mechanism of a power plant, we must look into very basic of the pressure versus temperature diagram of the phase diagram of ice, water and steam. Okay. And you must have noticed that there are some critical point exist in this diagram. Please have a look. This is a saturated vapor pressure curve of a solid ice with the gas, and this is the liquid. And the critical point here is defined as that beyond this temperature where the water and steam you cannot really distinguish. So, we have a chance to go into the supercritical region where we will get a higher temperature which need higher pressure. So, if you want to mean that if you want to boil a water at higher temperature, you have to input a higher pressure, means the vessel itself should contain higher pressure. So, material should survive such higher pressure, means you one hand have steam which may corrode the material, at the same time you have higher temperature and higher stress. So, all these three, corrosive environment, higher temperature, higher stress, all are involved. So, in this case a higher corrosion and higher creep resistant steel is required. And now, the efficiency will increase if you go along this direction. Okay. Now, let us have a look from 1960 or this time. Here there are some digits are shown where 167 is basically the pressure in terms of bar, and this is the temperature range which is operated. So, we can go into this higher side actually, and day by day people develop material to go into more and more operating temperature higher side. So, let us say during this time we use mostly the upper or ultra supercritical critical technology. Okay. So, here the steam condition increases and material development milestones are shown here, where we expect and we need to develop material which can be used as a much higher temperature and much higher pressure, so that the efficiency of the Carnot cycle will increase, or we can extract more amount of heat or more amount of power or more amount of electricity out of that cycle. So, therefore, the demand of the material is very clear at this moment. Now, to discuss about this material, we need to understand what are the alloying addition to be done in a steel. Usually, any alloy addition or alloying element can be classified into two major categories. So, one element could stabilize the ferrite. Ferrite is a alpha, okay, alpha phase which is a BCC in structure, or the element which can stabilize the austenite phase which is a FCC structure. So, therefore, the steels also classified into ferritic steel with a BCC structure or austenitic steel with FCC crystal structure. It is very clear. Now, the alloying element also can be categorized as a ferrite stabilizer or austenite stabilizer. However, to understand this, we need the help of a diagram which you already have learned, maybe learned in a physical metallurgy classes, which is called as Seifert's diagram. What this diagram said? Here this is the nickel and this is the chromium content, and we can get what chromium content or what nickel content which phase is stabilizes. However, only nickel or chromium is important? No, there could be other alloy additions which may be expressed in terms of nickel equivalent or chromium equivalent, means it has the same effect as addition of nickel. Okay. And nickel is a FCC FCC structure and chromium is a BCC structure. So, from here itself it is clarified that if we add chromium, then ferrite will be stabilized, and if we add nickel, then austenite is going to be stabilized. So, here from starting from 0, if we go along this direction, you will see above 25% of addition of nickel, here everything is austenite. On the other hand, along this side, if we go above 15% of chromium, then I will also get the ferrite. However, here what we call it as a ferrite is a delta ferrite, means that high temperature ferrite we are talking about, means a higher lattice parameter. However, in the lower side we will get the martensite, okay? And these are the domain which overlap between two different phases, okay, where a particular domain at high nickel and high chromium containing steels are often called as a duplex steel. This is a diagram which are often used for stainless steel, because stainless steel is a heavily alloyed steel. Now, so from here if we need to design a ferritic steel, we could easily understand that we need a chromium equivalent which can be higher, or if we need to develop a austenitic steel for higher temperature application, then we have to go into this side. Okay. Now, let us see what are the alloys so far has been developed and where those domain actually exist. Now, here you see I show you 4 major types of heat resistant steel and their domain of the composition where they are stabilized. So, the one stands for the ferritic. Yes, this is the ferritic steel domain which is shown here as 1, and the 2 is the martensitic grade steels. Okay. This is the martensitic and this is the ferritic. And for austenitic grade corrosion resistant steel, the domain is here, so far has been developed, and this is a very special high strength austenitic steel which has relatively high nickel and high chromium content. So, let us now start our discussion with the ferritic heat resistant steel, what is expected and what we have developed so far. Now, the ferritic heat resistant steel are basically high chromium and low carbon containing steels. Here these alloys are developed to provide resistance to high temperature corrosion. So, the high temperature corrosion and oxidation, they must be coupled with. We are talking about the alloy addition here. So, from the diagram or the Seifert's diagram itself, one can assume that the chromium percentage should be somewhat around 15% chromium is required, around 15%. Okay. And there the nickel is very less. Okay. So, since chromium is a ferrite stabilizer and therefore, we basically stabilizes the ferrite which is a low temperature phase at higher temperature, because the application temperature is higher, and we are talking about ferritic heat resistant steel means that the during the operation itself the ferrite phase should get stabilized, and therefore, the strengthening by heat treatment is not really possible. However, we can go for addition of silicon and aluminum, small amount of some rare earth element which reduce the oxides valuation. You have already discussed that yttrium and cerium and so on, they have some pegging effect or mechanical keying effect which give a good adherence of these alumina which appear at higher temperature on the surface of the material and give us a good protection for high temperature exposure. And therefore, these addition can be done with silicon and aluminum. However, carbon content is very low, and therefore, the excellent oxidation resistance and therefore, the excellent oxidation resistance we can achieve, which we have also discussed in iron, chromium, aluminum alloy. This is also a ferritic heat resistant steel, because chromium content is high, okay, and aluminum is added, so that we get a alumina scale on the surface, and this is the reason. Now, let us have a look at some of the very important ferritic heat resistant steel. Very initially iron 6 chromium was developed, and the temperature capability was 650 degree centigrade, which still now used for petrochemical, but the derivative of those elements of those alloys came like 10 chromium, 2 silicon, and these are somewhat very important alloys. You have seen that it has been derived from those basic grade steels, which use for heat resist heat treatment furnace equipment, or let us say some of the chemical plants or like petrochemical plants today, which can survive at such a very high temperature around 1000 degree centigrade, or even we can go for 1400 degree centigrade, because steel is cheaper and we only need some heavy alloy addition. So, 25% chromium to be added. However, it requires very special attention during the alloy processing itself, so that the chromium should be in the alloyed condition, not as a chromia or other carbide formation should be avoided, and very little amount of rare earth elements are added, so that we get a good pegging effect and avoid the spoliation of the scale. So, this is one of the very important category of the steels of the ferritic category. Now, let us talk about the martensitic creep resistant steel. So, the name itself said again that they contain martensite microstructure. Okay. And now, what is the operating condition of the steel? Yes, it should be minimum something like 500 or 600 degree centigrade. So, the martensite phase should be stabilized, but is it possible or not, that is another question. But let us look at what is desired out of those steel. The microstructure content tempered martensite, means before application the martensite is tempered, and during tempering operation we get some carbide precipitate. So, alloy addition should be done in such a way that we get a good distribution or homogeneous distribution of very fine carbide, which are not at all soluble in the matrix even at a very high temperature. That is basically the purpose. Now, the use here is the power plant that I said, and this power plant means either it could be critical, subcritical or supercritical temperatures, and the screep strength has been alloyed as a main pressurized part of this supercritical power plant, where the temperature rise even something like 590 or 600 degree in a martensite steel. So, this is the expectation, and with time people have derived so many different steels. You can see that chromium content here in the martensitic steel should be lower than the 15%. So, here it is expected that we have somewhat like less than 12% are there, and those initial those steels has little niobium content, you can see, okay, and nitrogen is not really very good compound, because it from nitride and brittle cracking. So, nickel is somewhat like 0.7 to 0.3. However, for this creep resistant steel we really do not need nickel at all. So, the next generation steels or advanced steels which has been developed as a martensitic creep resistant steel are the P91 grade steel, where this is a 9 chrome 1 moly steel. This is a very famous 9 chrome and 1 moly steels. So, here molybdenum has an effect on solid solution strengthening, and we added also for forming some carbide. So, here you do not see except niobium and vanadium other carbide formats. However, this is another advanced steel HCM12, here 12 is basically the 12 chromium, and molybdenum is slightly reduced. However, tungsten is added. Tungsten is added here, so that we get actually the good use of this tungsten carbide or maybe other Lavis phases. So, if you look at the applicability of this steel and the rupture time of 10 to the power 5 hour. Okay. So, here the temperature of application of this low chromium 1 moly steel is somewhat here, where P1 grade steel, P91 grade steel has been improved from the 9 chrome 1 moly. This is a modified grade steel actually than the simple 9 chrome 1 moly, and this HCM 12A can be operated at much higher temperature range, because this is a very advanced material or advanced steel that has been used in these power plants. So, the other purpose that we must discuss, that what are the precipitate expected from these P91 or these advanced steels. So, if you kindly have a look at the 12 chrome moly vanadium here, there are M23C6 carbide, and this is a precipitation hardened alloy with due to tempering of the martensite, whereas P91 has this Lavis phase which has been precipitated during creep itself, whereas some of these nitride or carbonitride precipitate that occur during tempering. And what we really do, that we basically there are some solution treatment in the austenite field, means we take the steel, we go to austenite phase field, we quench it, we get martensite, we then temper it, so that we get the desired precipitate type in order to strengthen the steel. P92 is also another derivative where we purposely add tungsten, so that we get this precipitation strengthening effect and so on. So, I show you one of these microstructure of such martensitic creep resistant steel. So, this is a transmission electron micrograph where you can see the precipitates, okay, and these are the dislocations. So, how the interaction of the dislocation and precipitate occur, and this is a steel after use, means this is a P92 grade steel, which is this one, which has been austenitized. This is the heat treatment schedule I am talking about, like 1000 degrees centigrade, tempered for 2 hours at 775. So, means we should expect some Lavis phase inside, and it has been creep tested for 6500 hour at 650 degrees centigrade, and then you see this microstructure. So, this is a length scale of 250 nanometer, and you can see that the precipitates are very fine, even though the Lavis phase is also in the nanometer scale. So, this is a Lavis phase which contain iron 2 molybdenum tungsten type Lavis phase, and you can see the finer microstructure, how fine the grains are of 250 nanometer, which is a typical tempered martensite microstructure. So, one hand we have the controlled nanostructure or precipitate, which gives us and retain the strength at high temperature, as well as we get very good creep resistance at higher or elevated temperature. So, martensite phase itself can be exploited as high temperature application, and people are using for power plant for very long time, even for a very long rupture time. And then the third category of these heat resistant steel has a austenite microstructure. Okay. So, austenite itself, you understood that austenite phase to stabilize, we need high nickel content and high chromium content. So, the steel itself content alloy addition to be higher, whereas there is a phenomena called as sensitization, you probably heard about, which occurred due to some of the precipitation at the grain boundaries. However, we can avoid precipitation at the grain boundary, where we get the carbide precipitate inside the grain body, so that it can avoid. So, alternative approach here to reduce the carbon content, like low carbon content, L stands for low carbon content. However, the general corrosion resistance of austenitic steel is much higher than the ferritic steels, that is already well proved, but the low resistance to stress corrosion cracking or pitting type of corrosions, and here molybdenum is used so that we added to improve the resistance to pitting like 316 or 317 type, or higher nickel content like Inco alloy 800 with let us say 20 chromium and 32 nickel. So, higher nickel and higher chromium is desired in order to avoid this stress corrosion cracking, and that is why you see those composition range why is that been selected. So, only to avoid these general engineering problems, and it is for sure that for 1% of creep strain for let us say 10 to the power 4 hour, these 25 chromium 20 nickel that gives us a higher strength level as well as a higher operating temperature. So, these austenitic steel with a high corrosion resistance are also important for this high temperature application. And since I said that the region of those earlier steel was lying here, that was a class 3 type, and here this is the austenitic steel with a very high strength. So, this has a very low domain, and where these materials to be used. Yes, when we need to use a material for brake, then we need both higher temperature, high wear resistance. A high wear resistance comes because of the higher strength, means hardness or red hardness is required. So, in that case actually, so the jet engines or turbine disc where disc alloy, these are the common alloy that are used from the for those kind of application. So, they are usually derived by precipitation strengthening or precipitation hardening by nickel 3 titanium aluminum type of precipitate. If you have a look at the very basic composition of tin dur, here we have nickel and chromium and we have basically titanium. So, titanium, nickel and aluminum, they basically form these precipitate which gives us a higher strength at a elevated temperature. And also the disc alloy is you can have a look with a reduced chromium, but the same nickel content with a slightly higher molybdenum, because people expect some precipitate of those molybdenum and so on along with those titanium aluminides. So, this is a very specifically designed with a very well composition range people use for the or engineers use for those higher temperature. So, with this today we finish our discussion on the steels that are used for power plant or various high temperature application, or let us say heating element, and in the next class we will discuss some more advanced alloys. Thank you.